All right, guys, Mr. Antonucci here, and this is section 5. We're going to talk about solving optimization problems. So, we've been talking about investigating max and min problems, and we're going to continue this theme and use calculus to solve optimization problems. Now, this process of optimization is the process of determining the best solution to a problem. And it's often going to be the one that maximizes or minimizes some quality or quantity, excuse me. So each problem is going to be different and unique in its own right, but there are some general steps that we can follow that will help us out um, with this. So here's our steps. Step number 1, we're going to read the problem until you understand it and can identify the quantity for which the max and min values to be found. Assign a symbol to represent it. Step 2, assign symbols to represent the other variables in the problem. If possible, draw a picture and label it, and determine the relationship among variables. Then you're going to want to express the quantity to be maximized or minimized as a function of one of the variables and determine a meaningful domain for the function. And then step 4, find the absolute maximum value or minimum of the function. So one of the tips for this is it's good to have in mind meaningful estimates of the answer. So have some ideas in your mind of what might make sense in the particular problem. And we'll look at that here. So here's an example of farmer with 400 meters of fencing wants to enclose a rectangular plot that borders a straight river. You can see it right here. If the farmer does not fence the side along the river, what's the largest rectangular area that can be enclosed? So first, the quantity to be maximized is the area. So we're just going to call it A. Okay. And then we're going to look at the dimensions of this rectangle. Oftentimes it's helpful to draw a picture. Here we already have the picture supplied, but a lot of times we're going to want to draw the picture too if that's appropriate for the situation. So we have the dimensions X and Y with the length of the side Y is going to be parallel to the river. See how they're parallel right there. So the area is XY. And because there are 400 meters of fence, this gives us another equation that we can use where 2x plus y should equal 400 because there's 400 meters of fence in this situation. Now, step 3, we're going to want to express the area as a function of x. So we can take our perimeter equation and solve it for x, and we get 4,000 minus 2x, and I mean, we could solve it for y. And then, so typically in these problems, you're going to have a primary and a secondary equation. The primary one is the one you're going to optimize. The secondary one is another equation that relates the quantities involved, but that you can solve for one of the variables. And then we're going to take that secondary equation and substitute it in to the primary one to get our primary equation all in terms of one variable. So this would be x times 4,000 minus 2x. Okay, if we simplify this, we would have 4,000 x minus 2x squared. Now, the domain of this function is going to be 0 to 2,000 given the context of the problem. Okay, because x represents the length of the perpendicular side of the fence right here. So it can't be 0, or it can't be negative rather. And it can't be so much that you use all the fence. So if x is up to 2,000, if it's more than 2,000, then it's going to make your y value negative, which doesn't make sense in the context of the problem there. Okay, so the number that maximizes this is going to be the number that maximizes our function a. So if we take the derivative, you get 400, or excuse me, 4,000 minus 4x, set that equal to 0, and you would get x equals 1,000. Now, this x equals 1,000 is our critical number, And so we need to make sure that this critical number is actually the max value. Since we have a closed interval, we can use the candidates test and determine which of the three values, the endpoints of the interval or the critical number that we got, which of those will give us the max area. So if we plug in 0 to the area function, you're going to get 0. If you plug in 1,000, well, 1,000 is going to give us 2 million. And if you plug in 2,000, that's also going to give you an area of 0. Because at the endpoints, at the endpoint of 0, you're not using any of the fence for the side X, you're using it all on side Y. So there's no area. Similarly, if X is 2,000, then you have those two sides and they're all using up the 4,000 feet of fence, or 4,000 meters of fencing rather. And so you're not going to have any area in that case. All right, so our max value is 2 million meters squared. So make sure when you write your answer in these types of problems that you give the units for the problem. Now, we could have also used the second derivative test here. So a prime, a double prime of x is equal to -4. And the second derivative is negative for all values of x, particularly at the critical number of 1,000. So we know that that is going to produce a relative max. All right. So let's move on to our next problem. This one deals with maximizing volume. So the from each corner of a square piece of sheet metal 18 centimeters on a side, we're going to remove a small square and turn up the edges to form an open box. What are the dimensions of the box with the largest volume? So in this situation, we know some of the dimensions of the piece of paper, or the of sheet metal rather. And so if you imagine we have a big square of sheet metal, we're going to cut out corners of the same size and then flip those sides up and make an open box. So the quantity to be um, optimized here is the volume. So we'll call that V. And then we're going to let X represent the side length of each amount that's cut out of each corner. Okay, because we're going to remove those. And then the side lengths of the sides that are being folded, that's where you see the dotted lines in the figure, we'll call those Y. So both X and Y in this context are in terms of centimeters. Now, Y is going to be equal to 18, which is the entire length of one side, minus twice X, because you're cutting, if you look at just one side, you cut X out of one side and X out of the other side. So the entire length of the cut side is going to be 18 minus 2X. So this can help us write the volume of the box, because we know that the volume is going to be xy squared in terms of this situation. Because once you flip those sides up, you're going to have the base of the box, which is y by y, and then the height of the box, which is the x value that of the side that you've now flipped up. So however far in you cut, when you flip it up, that becomes the height. So length times width times height, it gives us xy squared. Now, we want to get this all in terms of x, so x equals 18, or excuse me, y equals 18 minus 2x, and we're going to square that there. Okay, so since both x and y have to be greater than or equal to 0, the 18 minus 2x has to be greater than 0, so the domain is going to be the closed interval from 0 to 9. In fact, oftentimes with these types of problems, you can make the domain the open interval 0 to 9, because if the x value is 0, then you haven't cut anything, you can't make a box. If the X value is 9, you've cut 9 centimeters from one side and 9 centimeters from the other side. You don't have a box anymore because you cut out the full amount from each half. So you can kind of reason that the interval is going to be an open interval from um, 0 to 9 in this case. But it's helpful to establish the domain, and we'll see why in a little bit. So now we want to get the derivative um, for this one. And we could do a number of things. We could FOIL that out and distribute the x, or we could just use the product rule. So I'm going to do the product rule with the chain rule on the 18 minus 2x squared. So that would be 2x times 18 minus 2x times negative 2, okay, plus 18 minus 2x quantity squared. All right. Now, if we simplify this out and factor it, we're going to end up getting 18 minus 2x times 18 minus 6x. All right. Now, we solve this derivative equal to 0. So this factor right here is going to give us x equals 9, and this factor is going to be x equals 3. Now remember, when we said the domain, the endpoints of the domain here are going to result in a box that has no volume because either you're not cutting anything out, so there's nothing to flip out, or you've cut both sides the whole way to the middle, so there's nothing left for the bottom. All right, so x equals 9, we can eliminate that, and then we just have one critical number. This is why the domain is important for our problem. Now, we can use either the first or second derivative test and determine whether the derivative, whether x equals 3, that critical number, is a relative max or relative min. It's probably going to be a max, but you have to show the work and justify that it's going to be a max. So if we use the first derivative test, the derivative is going to be less than or greater than 0. Let me erase that. The derivative is going to be greater than 0 for x less than 3. Okay, if you plug, like, let's say you plugged in 1, then you would have 18 minus 2 times 18 minus 6, which is going to be a positive number. And v prime of x is less than 0 for x greater than 3. If you plug a number bigger than 3 in, you're going to have a negative times a positive, which is a negative. So since the first derivative changes from positive to negative at x equals 3, you have a relative max there. And then we evaluate the original function at 3, and you would get 432. And the units are centimeters cubed because we're talking about volume. And then you could state your answer. The max volume of the box is 432 centimeters, and the dimensions are a base of 12 inches and a length and width of 12 inches and a height of 3 inches. Okay? All right, so now we're going to look at another problem where we're going to try to maximize the area. So let's read the setup here. Manufacturer makes a flexible square play yard with hinges at 4 corners. So it can be, you can create it into a box like this, like a square. And it can be opened at one corner and attached at right angles to a wall or side of a house, like we did here. So 2 of the sides would be here, and then these are the other 2 sides. If each side is 3 meters in length, the open configuration doubles the available area from 9 to 18. Is there a configuration that will more than double the play area? So what we could do is these 2 sides in the middle here, we could like pull the corner out and make it like a triangle on top of a rectangle here. So we want to know, um, is this what is going to be the optimal area of the play yard? So the quantity we want to maximize is the area. And since the play yard has to be attached at right angles, the possible configuration is going to depend on the amount of wall used as the fifth side. So the amount of wall used right there. So what we're going to do is kind of divide the play area into two sections. So with a rectangle here, um, and a triangle. All right. So the play area is going to be the sum of those two areas. So the area of the triangle, excuse me, the area of the rectangle, let me just write this here. If you look at this rectangle right here, it's 3 by x, okay? But the region is symmetric, so there's two of them. So this would be 6x. So that's the area of the rectangle plus the area of the triangle. We have a triangle here and a height there. So the base of the triangle, so the area of the triangle is going to be 1/2 base times height. The base is going to be 2x. And the height of the triangle right here by the Pythagorean theorem is going to be square root 9 minus x squared. So that simplifies to x square root 9 minus x squared. And that represents the area of the triangle. So at the top, so we have square root uh, x times square root 9 minus x squared. All right. So the domain here is going to be the interval from 0 to 3. All right. Because if you have anything smaller than 0, then it doesn't make sense in this situation. And anything bigger than 3 is not going to work out for the side length x, or it'd be longer than the side. Actually, we can include the endpoints here, and we'll see why in a little bit. Okay, so the max area of the play yard, we got to find the critical numbers of our function. So let's take the derivative. The derivative of 6x is just 6 plus. Now we got to do the product rule. So derivative of the first is x times the second. Derivative of the x is 1. So 9 minus x squared plus the first times the derivative of the second. And if you've noticed the square root, we call it the square root trick. It's the derivative of the inside over twice the original square root. Only works for square roots. Okay. The 2's are going to cancel here. And we have 6 plus square root 9 minus x squared minus x squared over root 9 minus x squared. Now we could do some algebra and simplify that and get a common denominator and add and subtract and everything like that. But we want to figure out where this is the critical numbers where a prime is either equal to 0 or undefined. And we can see right away that the function is going to be undefined when x equals plus or minus 3, because that makes the radical, the denominator of the radical um, equal to 0. All right, but we can throw away the x equals -3 because that is not part of our domain. Okay, so moving along here, if we set this equal to 0 and then solve, we can kind of go from there. All right, so I'll show you how to do that. So one of the easier things you could do here in this situation is graph the derivative, and I'll show you here. So we're graphing this, and then the critical number when the derivative right here is equal to 0 is 2.79181. Okay, so um, we're going to go a prime of x equals 0 at x equals 2.79181, which is 2.792 if we round to two decimal places. Okay, and then we could just use the candidates test. If we evaluate the area at 0, you're going to get 0. Okay, essentially just plugging 0 into this equation. If you evaluate at 3, you're going to get 18. And if you evaluate the function at 2.79181, you're going to get approximately 19.817. Now, I will say, because the 2.79181 is not your final answer, you're going to want to not round that. You want to go out as many decimal places as you can, and then use that to get your final answer for the area. Okay, so the original question that we were asked here is there a configuration that will more than double the play area? So using a wall length of 5 point, what's it going to be? So the wall length was 2x. So that's 2 times 2.79181, which ends up being 5.584. That's going to more than double the play area. So that is going to be our optimal dimensions for the play area for that one. All right. So that's it for this one. Let me know if you have any questions, and take care.